Hello everyone, welcome back to another online lecture. Today we are going to be learning about section 11.3 from the Briggs textbook. And this section concerns this concept called a Taylor series. Alright, so without further ado, let's just go ahead and jump into it. Also, I'm recording this on a different platform other than the PowerPoint app, and so hopefully it works out a little bit better. Alright, so let's do some review first. There are two things that we have learned up to this point. In chapter 11, the first thing we learned in 11.1 was this idea of a Taylor polynomial. So a Taylor polynomial centered at a point A is defined as f of A plus f prime of A times x minus A plus f double prime of A divided by 2 factorial times x minus A squared. And this continued until we got to the nth term of this Taylor polynomial, fn of A divided by n factorial times x minus A to the nth power. This could be written a little bit more simplistically if we write it in summation notation. If we were to write this as the sum from k equals 0 to n of fk of A divided by k factorial times x minus A to the kth power. And remember the purpose of a Taylor polynomial. A Taylor polynomial's purpose is to approximate the function f of x. It's going to match f of x's 0, first, second, and nth derivative all at the point A. Remember, a 0th derivative is really just the y value. So the claim is that this Taylor polynomial has the same y value at x equals A as the function f of x. And in fact, we showed that they both had f of A as their y value. All right? And so the idea is that a Taylor polynomial approximates a function. Okay? The thing that we learned in section 11.2 was that a power series is defined to be a series of the form sum from k equals 0 to infinity, an infinite sum, of ck times x minus a to the k power. The reason we call this a power series is because it has powers of x minus a, an infinite sum of powers of x minus a. We discovered that a power series represent functions. They only converge on a particular interval. So we discussed that sometimes power series converge at a single point. Sometimes they converge on a finite interval of length r, or of radius r. And sometimes they're the entire real line. They converge for all x. Those were the three cases that we discussed. So just a quick example as a reminder. This is a power series here because we have powers of x minus a to the k. And in fact, we discussed that this particular power series could be written as 1 divided by 1 minus 2x whenever the absolute value of 2x is less than 1. And that occurs if and only if the absolute value of x is less than 1/2 if we divide both sides by 2. All right, another way to kind of see this is that this power series here it's basically a geometric series where this 2x is your r. You can kind of think about that as your r. It's raised to the kth power. So this will converge only if this r is less than 1. The idea behind 11.3, and this is really a remarkable section, it's one that has profound implications throughout all of mathematics, is that we're going to combine these two ideas. The idea of a Taylor polynomial and a power series combined together to create this thing called a Taylor series. So instead of just approximating a function using a Taylor polynomial, we're going to extend this polynomial infinitely to get an exact representation for the function. So let me just demonstrate the idea here by first starting with some definitions. A Taylor series is just a Taylor polynomial extended infinitely. So instead of stopping it in here, we replace that with an infinity. If the center is 0, in other words, a is equal to 0, then the series is called a Maclaurin series. All right? So if you ever hear someone say Maclaurin series, all we're saying is that it's a Taylor series centered at a equals 0. And a Taylor series is really just a special type of a power series. And it's going to be very useful for us coming up shortly. So the formal definition given by the textbook is this thing. We're going to suppose that f has derivatives of all orders, so it can be differentiated infinitely many times, on an interval that is centered at the point A. The Taylor series for f centered at A is, of course, just f of a plus f prime of a, x minus a, plus f double prime of a divided by 2 factorial times x minus a squared, and this continues on infinitely. And as you can see here, this is the way that it's written in summation notation, with an infinity as the top bound for that sum. All right, so a Taylor series centered at 0, of course, is called the Maclaurin series. And then one other thing to note, which I'm not sure I've talked about yet, is that 0 factorial, by definition, is going to be equal to 1. If it weren't equal to 1, we would run into problems. And so we're just going to define 0 factorial as equal to 1. The main idea behind this section is ultimately going to be finding Taylor series for various functions. And so I'm going to give you functions and then ask you guys to find the Taylor series for them. So let's give it a shot. In this first example, we are going to find the Maclaurin series for cosine of x. All right, so in section 11.1, we already discussed what the Taylor polynomial for the cosine of x is. And we'll see it again here, except now it's extended infinitely. But just so that way we cover all of our bases, I'm going to start at the beginning, where it'll feel the same as if we were in section 11.1, where we're finding the Taylor polynomial. Okay? So the first thing that we do is we write out a bunch of derivatives, and then we are going to plug in our center. Since we are working with the Maclaurin series, this means that a must be equal to 0. So we're going to compute f of 0, and that's just cosine of 0, which is 1. We're going to compute f prime of 0, that is just negative sine of 0, which is 0. We're going to compute f double prime of 0. That is negative cosine of 0. That is negative 1. And you guys remember this process. We took some time to do this in section 11.1. And f4, 0 is, again, cosine 0, which is 1. And it just repeats this cycle. So one thing that we might notice here is that all of the odd order derivative terms are 0. Right? So if we took the first derivative, the third derivative, fifth derivative, seventh derivative, they're all 0. So this is the derivative calculations. The next thing we're going to note is just what the general way to write a Maclaurin series is. So in general, the way that we write a Maclaurin series is going back to this slide. We're just going to copy this thing down, except with a equals 0. Whoops. Oh, nope, that's not what I want. Let's go back. Alright, sorry about that. It is the sum from k equals 0 to infinity of fk of 0. So instead of a, we plug in 0 there. K factorial times x. Normally we would say minus a. Since a is 0, we just say x raised to the k power. And we can actually get rid of the parentheses. So let's clean that up a little bit. X to the k. We can write this out. We can say this is f of 0 plus f prime of 0 times x plus f double prime of 0 divided by 2 factorial times x squared plus f triple prime of 0 divided by 3 factorial times x cubed plus, and this extends forever on. So this is the general way that we write a Maclaurin series for just an arbitrary function f of x. We're now going to use this to write down our Maclaurin series for cosine of x. So the first thing is f of 0. Let me actually do this. This is a convenient way of using this, this app as opposed to the PowerPoint slides. Now I can show you part of the previous one. Okay, so for cosine of x, f of 0, of course, is just 1. So we're going to start with a 1 here. F prime of 0 was equal to 0. And so we would just get rid of this whole term. Similarly, this this third derivative term was 0, and so we get rid of that one. This f double prime of 0 was equal to negative 1, and so what we have is minus 1/2 x squared. And then if we were to continue this process, what we would get is plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th plus 1 over 8 factorial x to the 8th. And then this continues forever. And this should look familiar, right? Because this is the Taylor polynomial for cosine of x if we stopped at 8, if n was equal to 8. And so if we want to write this with a summation notation, then the way that we might go about doing that is by saying the sum from k equals 0 to infinity. Let me just go ahead and write what the general form is. This is fk of 0 over k factorial times x to the k. We would write it, in this case, as k equals 0 to infinity. This will look a little bit weird, but the idea is that if you want to write this in a sum, notice that we only have even powers of x. We only have x squared, x to the 4th, x to the 6th, x to the 8th. So the way that this is written as a sum, and also notice that the terms alternate. We have a negative, positive, negative, positive. This one should have been negative. And so they alternate. And so if we want to alternate the terms, we're going to have a negative 1 to the k. And yes, this is negative 1 to the k because the first term is positive. And if we want to express only even powers for x, then the way that we're going to do that is by writing x to the 2k. Okay, so let's think about why that is. Whenever k is equal to 0, so if k equals 0, then we would get x to the 0. If k is equal to 1, we would get x to the 2 times 1, so x squared. If k is equal to 2, we would get x to the 4th, and so on and so forth. So that's why we can write x to the 2k there. That captures just the even powers of x. And then if we divide this, notice we have the same thing happening with these denominators. We can write this first one as 2 factorial. We have 2 factorial, 4 factorial, 6 factorial, 8 factorial. And so we can write this as 2k in parentheses factorial. And so the conclusion here is that this is the Maclaurin series for cosine of x. And so if we want to write down the Maclaurin series for cosine of x, this is what we would do. All right, so in order to find the interval of convergence, remember in section 11.2, we found interval of convergence by using either the ratio or the root test, one of those two. In this section, we are going to almost exclusively use the ratio test. And the reason that we use the ratio test here is because we have a factorial in the denominator. And this is going to occur for pretty much all of our problems, which indicates that it will be much easier to use the ratio test from the beginning. All right, so by using the ratio test, we need to define R to be the limit as k approaches infinity of ak plus 1 over ak, where ak, where should I write this? We're going to define it up here. ak is equal to negative 1 to the k times x to the 2k all over 2k factorial. Great. So, ak plus 1 is not a super trivial calculation. Let's think about it. ak plus 1, we just substitute a k plus 1 every time we see a k. So we get negative 1 to the k plus 1 times x to the 2, and in parentheses we're going to write k plus 1. It's very important. And whenever we have 2k factorial on bottom, we will replace that with 2 times k plus 1 factorial. That k plus 1 is still in parentheses. We can rewrite all of this as negative 1 to the k plus 1 times x to the 2k plus 2 divided by 2k plus 2 factorial. Okay. So now let's substitute that in. We're going to have negative 1 to the k plus 1 times x to the 2k plus 2 divided by 2k plus 2 factorial times 1 over ak. So in this case, that will be 2k factorial divided by negative 1 to the k times x to the 2k. Alright, so one thing to notice is that since this is all in absolute values, these negative 1 to the k's just basically disappear, because inside absolute values, negative 1 to the k is just 1. Next, notice that we have x to the 2k plus 2 and x to the 2k. That will simplify to just be x squared on top. Okay, so we get x squared, and then notice that on bottom, or rather we have the fraction 2k factorial and 2k plus 2 factorial. That 2k plus 2 factorial can be rewritten. I'll go ahead and spell out this step in its entirety as 2k plus 2 times 2k plus 1 times 2k factorial. And these 2k factorials will cancel. All right. And so what we are left with is just the limit as k approaches infinity of the absolute value of x squared all over 2k plus 2 times 2k plus 1. All right, since this is a limit as k approaches infinity and x is not k, we can bring that x squared to the outside of the limit. So let me do that here. This is equal to x squared times the limit as k approaches infinity of the absolute value of 1 divided by 2k plus 2 times 2k plus 1. And of course, that limit is just equal to 0. And so what we end up with is x squared times 0, which is just 0. And so the conclusion here is that since we are using the ratio test, and we get 0 as an answer for our ratio, since this is less than 1, this will converge for all values of x, because it doesn't depend on x to make this fraction less than 1. So the conclusion, let me write it down. Since r equals 0, which is less than 1, for all x, this sum from k equals 0 to infinity of -1 to the k times x to the 2k over 2k factorial converges for all x. And we can write down that the interval of convergence is -infinity to infinity. And if we wanted to write down the radius of convergence, we could say that that is infinity as well. Okay, so the idea is that whenever you are asked to compute the interval of convergence, just use the ratio test. All right, so let's continue. So let me just make a couple remarks before we continue on to our next example. The hardest part of this sort of process, and it may not have seemed like it in this particular case, because it was actually kind of trivial, is finding a way to write down fk of a. So the kth derivative of f evaluated today. On the previous example, we were able to figure out that the kth derivative of our function evaluated at a was, and I'm going to walk through you guys with this, it was what we did here. This process was what we used to figure out what fk of a is. Specifically, we noticed that for the odd terms, it was 0, and for the even terms, it alternated. And so, if we want a general way of expressing the kth derivative of our function evaluated at a, in this case a was 0, that's basically what we are going to write down here. So for the odd terms, we got 0, and for the even terms, so this one will look a little bit weird, but we notice that it alternated, but it alternated only on the even terms, right? So we can't just say -1 to the k because it alternates only on the even terms. And so to get this to work out properly, we're not going to say -1 to the k, but -1 to the k over 2. And that will capture the alternating on the even terms. All right, so the hardest part of doing this sort of process is finding a general way to express this kth derivative of f evaluated at a. And you'll see why this is the case on the next example that we do. So just a side note, have you ever wondered why functions are called even and odd? Remember that an even function is one that has symmetry about the x-axis, and odd is a function that has symmetry about the, an even function has symmetry about the y-axis, an odd function has symmetry about the origin. I'm pretty sure that sounds right. And so, in general, in this particular case, we know that cosine is an even function, and you'll notice that cosine only contains even powers of x in its Maclaurin series, so that's why it's called an even function. And then the Maclaurin series for sine of x, if we were to actually compute that out, only contains odd powers of x, which is why sine of x is an odd function. And if we change the center of that function, the Taylor series might be even, odd, or neither. So we can make no guarantees if we were to use a equals 5, or a equals 10, or a equals -1. All right, so that's just a fun little side note. So let's do this example now. We're going to find the Taylor series for 1 over 1 minus 2x centered at a equals 3 and its interval of convergence. So one thing I'll note here is that we would know the Taylor series for this guy already if a was equal to 0, because we already actually have the power series representation for 1 over 1 minus 2x. That is what we discovered in section 11.2. When a is equal to 0, we could write this thing as the sum from k equals 0 to infinity of just 2x to the k. But that is not the case here, because a is equal to 3, this Taylor series is going to be a little bit different. So the hardest part, as I just told you, is finding some way to express the kth derivative of f evaluated at a. So what we are going to do is we are going to figure out a way to write that down in a sort of pattern. So let's consider the following table. Oh, this is so nice. Okay. Over here on the left, we have k. And then here, in this portion of the table, we're going to consider the kth derivative of our function evaluated at x, so just a regular derivative. And then over here, we're going to consider plugging in 3. Eventually, the hope is that we recognize a pattern so we can express, in general, the kth derivative in a particular way. So let's give it a shot. I'm going to change to a dark green. So let's just throw in some values for k here. Whoops. I think I need to actually give myself a little bit more space between these. All right, so for k equals 0, that just basically means write down your function and plug in 3. We're not taking any derivatives. We're just going to get f, let me continue with the green, f of x equals 1 over 1 minus 2x. All right, great. We could also rewrite this. This will be helpful for us in a second as 1 minus 2x to the -1 power. Okay, over here on the right, if we want to plug in f of 3, this is just going to be 1 divided by 1 minus 2 times 3, so 1 minus 6, which is just -1/5. All right. Next, we're going to take a derivative of this function. So the derivative of this function, it's easier if we think about the derivative of this function, which is equivalent, we have to use the chain rule here. And so using the chain rule, we bring that negative 1 out front. So we have negative 1 times 1 minus 2x to the negative 2 power times the derivative of the inside, which is negative 2. And this can be simplified. We can rewrite this as 2. Let me give myself a little bit more space here. I think I actually need to move all of this over as well. Okay, we can rewrite this as 2 divided by 1 minus 2x squared. And we could once again rewrite this, if we wanted to, as just 2 times 1 minus 2x to the negative 2. Okay, and then if we plug in 3 into this, what we'll end up with is 2 divided by 1 minus 6 squared. And so we could write that as just 2 over negative 5 squared. So I am intentionally not going to simplify this, just so that way I can find a pattern later on. Alright, so for the second one, if we are taking the second derivative, we are going to look at this guy to take its derivative. And if we take the derivative of that, we bring that 2 out front. And so we can write this as negative 2 times 2, once again, not simplifying, times 1 minus 2x to the negative 3 power times derivative of the inside, which is negative 2. Can rewrite this entire thing as 2 times 2 times 2 divided by 1 minus 2x to the third power. Okay. If we plug in 3, we're going to get 2 times 2 times 2 divided by 1 minus 6 to the third power, which is just 2 times 2 times 2 divided by negative 5 cubed. Alright, so rather than working through some of the more difficult computations down here, let me just skip and give you some answers. If we were to compute the next derivative, we would get 2 times 2 times 2 times 2 times 3. This 3 comes from the fact that we'd have to pull this 3 down, divided by 1 minus 2x to the fourth power. And then over here, the third derivative, evaluated at 3, would be, of course, just 2 times 2 times 2 times 2 times 3 divided by negative 5 to the fourth power. And if we want to calculate the fourth derivative, this is going to be 2 times 2 times 2 times 2 times 2 times 3 times 4, all divided by 1 minus 2x to the fifth power. And over here, we get that same numerator, a bunch of 2's. Let's see how many. There's 5 times 3 times 4 divided by divided by negative 5 to the fifth power. Let me clean that up. All right. So Let me change the color of some of these 2's to give you guys a little bit of an idea on how to see this pattern. So I am going to color this 2. Let's color it orange. We're going to color these 2 2's orange. All right, let's now do 3 on this one. 4 on this next guy. And let me also color the other part of this numerator a little bit differently. Let me give that, oh, I don't know. Let's go for a purple. Is that, yeah, Clemson colors. It's the hardest decision I've had to make all day. All right. So that one didn't work. Great. So one thing that you might notice in the quest to find a pattern, if we want to eventually write the kth derivative of this function, like how do we do this? In general, the strategy is to write out a bunch of small derivatives and find the pattern that you can then use to write the kth derivative of our function, because that's what our quest is to do. We are trying to find a general way to write the kth derivative. Okay? So, one thing you might notice is that in each one of these integral or derivative calculations, we get an additional 2, right? And so, what we can say, and in fact, the number of 2's that we get directly corresponds to the derivative that we took. So there's 1, 2 here, we took the first derivative. There are 2 2's here, we took the second derivative. There are 3 2's here, we took the third derivative. 4, 4. So what that indicates to us is that we can write this as 2 to the k. Similarly, we notice that this 2 and this 2 times 3 and this 2 times 3 times 4, those are basically just factorials. And so we can write that as k factorial. So whenever we were taking the second derivative, we were calculating 2 factorial. Whenever we were on the third derivative, we were calculating 3 factorial. Fourth derivative is 4 factorial. And we notice that this even makes sense whenever we were in the first derivative, because really what we would have had here is just times 1. And 1 factorial is just 1. It even makes sense at the 0th derivative, because we would really have times 0 factorial. And 0 factorial is just 1. Alright, so let me go back to my green. And the denominator, I think, is fairly straightforward. The denominator actually changes pretty obviously. We always have 1 minus 2x raised to some power. And that power is always going to be 1 more than the derivative that we took. So here, this whole thing is raised to the 1 power, but we were at k equals 0. This whole thing was raised to the 2 power, but we were at the first derivative. And so in general, we can write this as 1 minus 2x raised to the k plus 1 power. And so what we have essentially done is we have figured out a way to express any derivative for this guy. If you just give me k, I can tell you exactly what the derivative is. If I want to calculate the 100th derivative, I just throw in k equals 100 into this thing. And the thing that we are actually looking for is not, in general, the kth derivative, but the kth derivative evaluated at 3, which is why we have this column over here to the right. because what we're really searching for is the entry that goes in this box. This is the key. We want whatever goes right there. So the thing that goes in that box, fk of 3, well, all we really have to do is throw in a 3 for this x, and we get our answer. Or, alternatively, another way of looking at it is looking at the pattern that emerged from these guys. You would get the same idea. So if you look at the pattern going down this direction, or if you find the pattern this way, you get this term, then you can go over here and just throw in your value. And the answer here is just 2 to the k times k factorial divided by negative 5 to the k plus 1. And let me throw some highlighter on it because this is the thing that is important. Whoops, don't want that. That is the thing that we are looking for. Okay, so the reason that we were looking for this thing was because we need to write, remember what the question was? I know that was a long time ago. We were trying to find the Taylor series for this guy. And in general, a Taylor series is written like this. So let's say, let me go back to blue. The Taylor series for 1 over 1 minus 2x is the sum from k equals 0 to infinity of fk of a divided by k factorial times x minus a to the k. So what we have just found is this term. We found this term of our Taylor series, and that was the hard part, was figuring out how to write, in general, the kth derivative of our function evaluated at a inside of our sum. And so we can then write that this is the sum from k equals 0 to infinity. We're just going to write now this thing. So we have 2 to the k times k factorial divided by negative 5 to the k plus 1 divided by k factorial times x minus a in this case was 3, so x minus 3 to the k power. All right, so we can do some simplification here. Notice that there's a k factorial on top and a k factorial down here, so those conveniently cancel. And so we can rewrite this now as the sum from k equals 0 to infinity of 2 to the k divided by, and I'm going to split that negative 5 to the k plus 1 into two pieces. I'm going to write negative 5 times negative 5 to the k. Make that a little bit clearer. Times x minus 3 to the k. And so we could rewrite all of this. Since we have a lot of things that are raised to the k power, notably we have a 2, a negative 5, and this x minus 3 to the k, we can just combine all of that together and get the sum from k equals 0 to infinity of negative 1/5 times 2 over negative 5 times x minus 3, that whole thing raised to the k power. And so this is the Taylor series for our function. It is precisely the Taylor series for this guy. And you'll notice that this does not look at all similar to what I was talking about earlier. This is not, the sum of just 2k, or 2x to the k. It is not that. And it looks a little bit different, and for good reason, because we had a different center. Alright, so next, what we're going to do, remember the second part of the problem asked us to find the interval of convergence. So in order to find the interval of convergence, we need to use either the ratio or the root test. This is one of the few instances whenever the root test is actually an okay option. The reason it's an okay option is because there are no factorials here. The factorials canceled out over here, and so we can use the root test. So let me switch colors. Convergence. Use the root test. So we define rho to be the limit as k approaches infinity of the kth root of the absolute value of negative 1/5 times 2 over negative 5 times x minus 3 all to the k power, close the absolute value, and finally we can simplify this. The kth root and the k power cancel out, but one thing that we should be extra careful about is that not everything is raised to the k power. This negative 1/5 is not raised to the k power, so we need to write that this is equal to 1/5 raised to the 1 over k power, because that's what happens when this kth root expands to that negative 1/5. And this is multiplied by 2/5 times x minus 3. Remember that the negative signs basically disappear because of the absolute value. And one thing that I should be extra careful about is that this x minus 3 is also still in absolute values, because we do not know yet what x is. X is still a variable, so we leave the absolute values around that. Alright, so then the thing that doesn't have a kth power, or the thing that doesn't have any k's in it, is this 2/5 times absolute value of x minus 3. So we're just going to pull this whole thing outside of the limit. We're going to get 2/5 absolute value x minus 3 times the limit as k approaches infinity of 1/5 to the 1 over k. This is really just 1 over 5 to the 1 over k. Alright, so as k approaches infinity, this one will look a little bit weird. As k approaches infinity, we get 5 to the 1 over infinity, which is 5 to the 0. So this entire limit, you might think it would have gone to 0, but this entire limit actually goes to 1. Alright, and if you don't see that, take a couple seconds to look at it carefully, because we get 5 to the 0, which is 1. Alright, and so we end up with just 2/5 times absolute value of x minus 3. Remember that we must set this thing less than 1 to figure out the interval of convergence. So now set 2/5 times the absolute value of x minus 3 less than 1. And so we multiply both sides by 5/2. So we get that the absolute value of x minus 3 is less than 5/2. And then remember, if we have absolute value of a less than b, then we basically just have negative b less than a less than positive b. So we get that this is negative 5/2 less than x minus 3, which is less than 5/2. We can add 3 to every side. So on the left-hand side, whenever we add 3, 5/2 plus 6/2 is just 1/2. On the right side, 5/2 plus 6/2 is 11/2. And so the interval of convergence is 1/2 to 11/2. Okay? And I'm not telling you the whole story here, because technically we would still need to test both of our endpoints. We would need to determine if 1/2 and 11/2 converged, but let's just take a look at what happens in the series right here. Think about what happens whenever you plug in 1/2 or 11/2. Well, if we were to plug in 1/2 right there, then we would get 1/2 minus 3, which is just negative 5/2. Negative 5/2 times negative 2/5 is just 1. So we get this whole thing would be 1. So we get 1 to the k, which is just 1. And so we get the sum of negative 1/5. And that diverges because of divergence test. You would get negative 1/5 plus negative 1/5 plus negative 1/5 infinitely many times. If we were to plug in 11/2 right here, 11/2 minus 3, well, that's just 5/2. We would end up with negative 1 right there. We get negative 1 to the k inside of our sum, and so that also diverges. And so technically, if we were on an exam, we should also prove that both endpoints diverge. But for the sake of time, I just omit that detail here. Okay, so that was a lot. Let's recap what this example did. We started off with this series, and we were asked to find we start off with this function, and we can call this f of x. And we were asked to find the Taylor series for it. Remember that the Taylor series for a function is its exact representation. So what I will claim is that this Taylor series is exactly equal to this function whenever x is between these two values. I haven't quite proven that to you yet. In fact, there's going to be something that we do a little bit later that proves that to you. But in the process of finding the Taylor series, the first thing that we had to do was we had to find this value, the kth derivative of our function evaluated at a. And to do that, we used pattern recognition, going in this direction or in this direction to figure out what our fk of a should be. And then we plugged it into our Taylor series, and we had these values as well, and we got this thing, we found the interval of convergence, and got that. Alright, so let's do another example. This time, we are asked to find the Taylor series for f of x equals 2 to the x, centered at a equals 3, and find its interval of convergence. And I give you a little bit of a hint here. The derivative of b to the x is the natural log of b times b to the x whenever b is a positive number. So in this case, our b is 2, and b obviously is positive here, so we can use this rule. Side note, if this was e to the x, then of course you know what that derivative is. It's just e to the x, and it also follows this rule. The natural log of e is 1, and so that's why this still works out. Okay, so we're going to do that same general process of figuring out a pattern to use. So let's see, how much space did I give myself? Gave myself just one slide for this. Great. All right, well, we'll make it work. All right, this time I'm only going to do one column of this table. I am only going to do this part of the calculation, and then at the very end, what I will do is I will get something here, and I can just plug in my x to figure out what fk of a should be. So let's label these. This is going to be k, and this will be fk of x. All right, so for k equals 0, we'll go up to 3 this time. 0, 1, 2, 3. Okay. All right, so the first one, our function is just 2 to the x. The first derivative of this is natural log of 2 times 2 to the x. The second derivative of this is natural log of 2 times the natural log of 2 times 2 to the x. So we can just write this as natural log of 2 squared. After that, it's the natural log of 2 cubed times 2 to the x. And hopefully by now you see the pattern. The idea is that this 2 to the x will always be there, so that's just unchanging. If we want to calculate the kth derivative of our function, then the basic idea is that in each one of these derivatives we add on an extra power of our natural log. And so this will just be natural log of 2 to the k power. And this is fk of x. So that is, in general, the way that you write the kth derivative of your function evaluated at x. So now we use this information. Let me actually write it below. I think that'll make the most sense. Right. So now I can write that fk of 3, because that's what a is equal to 3, is equal to natural log of 2 to the k, and anytime I see an x I replace it with a 3, so we just have 2 cubed, which is 8. So we can write this as 8 natural log of 2 to the k. And this was the big kicker. This is what we wanted to find. So let me put a cloud around it again to show that it's important. Great. So let's now write what the Taylor series should be. Taylor series for f at a is the following. It is the sum from k equals 0 to infinity. Let me write out in general what it should be. It's in general fk of a divided by k factorial times x minus a to the k. In our case, if we plug everything in, that's the sum from k equals 0 to infinity. Fk of a is this thing that we found down here in the cloud, which is 8 natural log of 2 raised to the k power. Note that the only thing raised to the k power is that natural log of 2, not the 8, divided by k factorial times x minus 3 to the k power. So that's our Taylor series. We did it. There's no simplification to do on this one. The only thing we could do if we wanted to is we could combine this power of k and this power of k together, but we don't have to. And so in order to find the interval of convergence, let's use the ratio test this time. And we use the ratio test because we have a factorial here. And so if we attempted to use the root test, we would be in big doo-doo. Alright, so we're going to define R to be the limit as k approaches infinity of the absolute value of ak plus 1 divided by ak ak plus 1 is going to, so first of all note that, let me just write in a light color, this whole thing here is your ak, and so ak plus 1, hopefully you guys understand the idea, is that we just add, instead of a k, we write k plus 1, so we have 8 times natural log of 2 to the k plus 1 power divided by k factorial times x minus 3 to, let me write that x minus 3 in the numerator, because that's really where it is, to the k plus 1 times, now if we divide by ak, we're going to get, whoops, this should be a k factorial. K plus 1 factorial, that's what I'm trying to say. Alright, over here we should have a k factorial divided by 8 natural log of 2 to the k power times x minus 3 to the k. Alright, this simplifies considerably. Notice first that these 8's will cancel. And then what we have is a natural log of 2 to the k plus 1 and a natural log of 2 to the k. That will just leave us a natural log of 2 on top. And also we have x minus 3 to the k plus 1 and x minus 3 to the k on bottom, so that just leaves us x minus 3 on top. And we have k factorial, k plus 1 factorial, that leaves us a k plus 1 on bottom. So all in all, this will simplify to, let's see, so we have the natural log of 2 times x minus 3 divided by k plus 1. Did I forget anything? I did not. All right, so with this definition of our limit, notice that the only place we see a k is right here. There's no k on top, so we could actually pull this entire numerator outside. What we would then get is just the limit of 1 over k plus 1, and that limit is 0. And so because of space, I am just going to write that this is equal to natural log of 2 times the absolute value of x minus 3. Remember, we keep the absolute values around the x part, times 0. And so this whole thing is equal to 0. And so the conclusion, of course, is that since r equals 0, which is less than 1, it doesn't matter what x I plug in, this thing will converge for everything. So since r is equal to 0, which is less than 1, for all x, this series from k equals 0 to infinity of 8 times the natural log of 2 to the k power divided by k factorial times x minus 3 to the k converges for all x. And so the interval of convergence we can write is negative infinity to positive infinity. Whew, that was fun. So that's another Taylor series example. The idea is we found this pattern. We were able to write down in general the kth derivative of our function. We plugged in 3. We got this thing. We threw this up here. Wow, that was a terrible way to do that. Right there. That's better. And so this was our Taylor series. We then used the ratio test to find the interval of convergence and concluded that it converges for all values of x. All right. So even though I've implied it a lot, technically it is possible for a Taylor series of a function to not be equal to that function. So sometimes a Taylor series is equal to its function. And in fact, in both of these examples, this Taylor series is exactly equal to 2 to the x. And this Taylor series, right here, is exactly equal to 1 over 1 minus 2x. And in this example, the Maclaurin series is exactly equal to cosine of x. But the idea is that sometimes this doesn't quite work. And there are some unusual examples beyond the scope of this course where the Taylor series will converge to some function other than f of x. I can't provide you with any examples off the top of my head. This is in a field of math that I'm not even that familiar with. But in order to prove that a Taylor series is equal to its corresponding function, we need to show that the, let's go to blue, that the limit as, let me make sure I get the right notation. Yeah, the limit as n approaches infinity of r n of x equals 0, where Rn is the remainder. All right, so this Rn is the remainder. Okay, and remember whenever we were figuring out the remainder theorem in the last section, the idea is that we can write the remainder like this. It is the n plus first derivative of our function evaluated at c divided by n plus 1 factorial times x minus a to the n plus 1, where c is some number between x and a. So that is our remainder. We need to show that that thing is equal to 0 for every x within the interval of convergence. Also note that if we were to instead show that the limit as n approaches infinity of the absolute value of Rn of x equals 0, that would work as well. And in fact, we'll do an example in a little bit that demonstrates this. All right, so let me just read through this theorem with you. Basically, it's what I've said already. Let f have derivatives of all orders, so basically infinitely differentiable. You can differentiate as many times as you want, On an open interval I containing a, so in this last example, that interval would be negative infinity to positive infinity. The Taylor series for f centered at a converges to f for all x within that interval if and only if the limit of the remainder is equal to 0 for all x and I, where this remainder is equal to this, and c is some number between x and a. Let's do an example. So a good portion of this example is spelled out for you already, but let's just kind of read through it. We're going to show that the Maclaurin series for the function e to the x converges to e to the x for x within negative infinity to positive infinity. So this is my interval of convergence. It's also the I that they reference here. So this I is this I. The Maclaurin series for e to the x, and I haven't formally proven this to you, but this is true. This is the Maclaurin series for e to the x. It's a very useful one. You will see this again, I am sure. It is 1 plus x squared over 2 factorial plus blah 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 all the way up to xn over n factorial, continued on indefinitely. And the remainder, Rn of x, is equal to fn plus 1 of c divided by n plus 1 factorial times x to the n plus 1. So let's think about this for a second. What is the n plus first derivative of our function evaluated at c? Well, first of all, any derivative of e to the x is just e to the x. So the n plus first derivative should be e to the x as well. If we plug in c, then it's e to the c. So this whole thing is equal to e to the c over n plus 1 factorial times x to the n plus 1. And of course, in this case, c is some value between x and a. Since this is a Maclaurin series, this is some value between x and 0. So then, we know that the limit as n approaches infinity of Rn of x is equal to, well, in this case, this e to the c is just some number, right? There are no n's in it, so we can pull that outside of the limit. It's treated as a constant. So we can write this as e to the c times the limit as n approaches infinity of x to the n plus 1 over n plus 1 factorial. All right, so now what is this limit equal to? Give you a couple seconds to think about that. This limit has to be equal to 0 because the denominator has a larger growth rate than the numerator. Because n plus 1 factorial grows much quicker than x to the n plus 1. And so what we have shown is that this limit, the limit of the remainder, is 0, which is what we wanted. We wanted to show that it was equal to 0. And since it is equal to 0, let's write out the conclusion statement. Therefore, we can definitively say that e to the x is equal to 1 plus x squared divided by 2 factorial plus blah 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 x to the n over n factorial plus, this continues on forever. It is equal to its Taylor series, to its Maclaurin series. And honestly, this is remarkable. Like, e to the x is a number raised to the, it's a number raised to the x power, and we're saying that you can write this as an infinite polynomial. I think that's amazing, right? It's kind of insane that we are able to do something like that because e to the x is some function that just looks like this. And I'm claiming that I can write that as an infinite sum of polynomial terms. I think that's really cool. All right, so the next one is we are going to show that the Maclaurin series for cosine of x converges to cosine of x for x within the real numbers. All right, so let's get cracking. We need to start by calculating the remainder. So let's do that. So the remainder in this case is Rn of x equals Fn plus 1 evaluated at c divided by n plus 1 factorial times, since this is a Maclaurin series, that means that a is equal to 0. So really this is just x to the n plus 1. Okay, so the next question is what in the world is this thing? What is the n plus first derivative of f at c? In the last example, this was really easy because any derivative of e to the x is e to the x. And so if you just throw in, or if you just take the n plus first derivative, you would just get e to the x, and then you can just plug in c. Here, it's not so easy because cosine of x alternates between cosine, negative cosine, positive sine, and cycles through those four infinitely many times. And so we cannot definitively write what this thing is equal to. We do know that it's plus or minus sine or cosine. So let me make that remark. Fn plus 1 of c is equal to plus or minus sine of c or plus or minus cosine of c. It is something in here. We don't know specifically what n is, so it could be any of those. All right, so how does that help us? Well, let's now consider the absolute value of the remainder. All right, so if we consider that, then here's something we know. We know that 0 is certainly less than or equal to the absolute value of the remainder. And this, let's see, how do I want to write this? Yeah. So this remainder, then, is less than or equal to m over n plus 1 factorial times x to the n plus the absolute value of x to the n plus 1. Remember that in the last section, we discussed that this m was the upper bound for the absolute value of f n plus 1 of c. All right, well, in this case, we know that an upper bound for fn plus 1 of c is 1. Because these functions, plus or minus sine of c, plus or minus cosine of c, never grow larger than 1. And so there's an upper bound for that. So in this case, since plus minus sine of c and plus or minus cosine of c are bounded by 1, m is equal to 1 here. Alright, and so this allows us to write down that 0 is less than or equal to the remainder, which is less than or equal to 1 over n plus 1 factorial times x to the n plus 1 power. Okay, so what next? Well, we need to compute the limit of Rn of x. So let's consider doing that. What I've essentially established with this chain of inequalities is something where we can use the Squeeze Theorem. If we take the limit of every side as n goes to infinity, then every side will go to 0. Notice that the limit of a constant is just equal to 0, or sorry, the limit of 0 is equal to 0. The limit of this guy, as we just discussed in the last example, is equal to 0 because factorials grow faster than exponents. And so that means that this limit in the middle must therefore go to 0. And so we conclude by Squeeze Theorem the limit of the absolute value of Rn of x is equal to 0, as desired. And so our final conclusion is that cosine of x is equal to its Taylor, or is equal to its Maclaurin series. Negative 1 to the k times x to the 2k divided by 2k factorial. These things are equal. And once again, this is kind of amazing because cosine of x is a trig function, right? It has to deal with triangles inside of a circle. And, you know, it alternates like this. It looks like that. And I claim that it can be written as an infinite sum of these polynomial terms. And you kind of saw that with the GIF that I showed you in the last video lecture where they progressively got closer and closer to this function of cosine of x. And so this is kind of amazing. All right, so there are lots of different Maclaurin series out there that are super useful for all of our calculations in everyday life. And one other thing that I will mention before I talk about those a little bit more is that anytime you get a calculator and you throw in a number like cosine of 5, for example, it doesn't know how to calculate that And so what it will actually do is it will use this Taylor series. It'll have to stop at some point. So I guess it'll technically be a Taylor polynomial. But it essentially uses this idea to calculate cosine of 5. You would just plug in 5 right here, and that is something it knows how to calculate. But it doesn't know how to calculate cosine of 5. It has to use this Taylor polynomial expansion idea. Okay, so there's lots of very cool Maclaurin series that are out there. On an exam, you guys will get these Taylor or these Maclaurin series if they are necessary. So we don't give you like this whole chart, but if there's a problem that requires, for example, the Maclaurin series for e to the x, then we would give that to you. And so, yeah, just looking at some of these, this series, which we discussed in section 11.2, is that geometric series. Basically, we can write this function as the sum from k equals 0 to infinity of x to the k, but only if the absolute value of x is less than 1. It doesn't work if it's outside of that. And then for this series, it's very similar. We just replace that x with a negative x, and we get this guy, once again, if absolute value of x is less than 1. E to the x, as we just discussed, can be written like this. Sine of the x has odd powers of x, so we have x cubed, x to the 5th. In general, odd powers of x. And the interval of convergence is all reals. Cosine of x is similar with even powers of x. For all reals, the natural log of 1 plus x. This is one we discussed a little bit in section 11.2. Its power series can be written like this. Negative natural log of 1 minus x can be written like this guy. And the inverse tangent function is one we discussed a little bit in 11.2 as well. It can be written like this. And yeah, lots of different functions. This is by no means a comprehensive list, and also this only talks about Maclaurin series. If you want to find a Taylor series, you're going to have to go back to this technique that we did in this example, where we had this function, and we threw in a equals 3, and we eventually got to an answer, and threw it into its Taylor series. So if you want a Taylor series, you're going to have to use something like that, and just go from there. But there's lots of super common Maclaurin series which are very useful. And frankly, I think that we're being a little bit nice on exams whenever we give this kind of thing to you guys, because whenever I took this course 4 or 5 years ago at the University of Missouri, we were asked to memorize all of these. And we had to use that on the exam. All right, so that's all I've got for you guys for this lesson. Hopefully you found it interesting, intriguing, and useful. Yeah, if you have any questions, feel free to just let me know in the comments or send me an email. I'm happy to answer. And until the next section, I will see you later. Have a good day.